This is a math Olympiad problem in which we're supposed to find all positive integers n, for each of which there exist two sequences of n non-negative integers that satisfy these equations. The solution of this problem is pretty hard to find, as it should be, since this is an Olympiad problem after all. But once the solution has been found, it's pretty easy to understand and to explain. If we rewrite the second equation in the form shown in this diagram, we can see that all the powers of 3 are odd integer numbers. And because in the left side of this equation they have coefficients 1, 2, 3, 4, etc. up to n, the odd-even property of the terms in the left side of the equation alternates. The first term is odd, the second is even, the third is odd, the fourth is even, and so forth. So, if we see that for some n the sum of terms in the left side is even, then such n can be eliminated, since the term in the right side of the equation is odd. We can see that for n equals 1 it works, because the first term in the left side of the equation is odd. For 2 it also works, because odd plus even is odd. But for n equals 3 it doesn't work, because odd plus odd is even. And for n equals 4 it doesn't work either, because even plus even is even. Since this pattern obviously repeats itself in every next group of 4 consecutive numbers n, we can conclude that the only possible n are numbers in the form 4m plus 1 and 4m plus 2. These are two actual sequences with n equals 1 and two sequences with n equals 5 that satisfy the conditions of this problem. It turns out that we need to look for valid numbers n only in the form 4m plus 1, because it's very easy to construct the sequences with n equals 4m plus 2 if we have such sequences for n equals 4m plus 1. We simply find a term in the existing sequence that has sequential number 2m plus 1 and break it in two terms to form the new sequence. If the exponent in the denominator of the existing term is k, then both new terms have exponent k plus 1. We will use the method of mathematical induction and will prove that if the proper sequences exist for n equals 4m plus 1, where m is not less than 2, then the proper sequences also exist for n equals 4m plus 13, thus skipping two numbers that follow 4m plus 1, that is 4m plus 5 and 4m plus 9. The method of constructing the proper sequences for n equals 4m plus 13 from the sequence with n equals 4m plus 1 consists of three steps that are easy to follow. The first step is constructing the proper sequence for n equals 4m plus 2, which we already know how to do. Then we'll start with two sequences for n equals 4m plus 2, and we'll add 11 more terms to each sequence with sequential numbers 4m plus 3, 4m plus 4, etc. up to 4m plus 13. For that, we will modify the term in the existing sequence that has sequential number m plus 2. If that term has denominator with exponent k, then we'll increase that exponent by 2, so that the new exponent will be k plus 2, and we'll add 6 more terms with sequential numbers 4m plus 3, 4m plus 5, etc., 4m plus 13, All 6 new terms will have denominators with the same exponent equal to k plus 3. You can easily verify that the modified term in each sequence is replaced with 7 terms whose sum is equal to the modified term. But we have 5 more terms with even sequential numbers: 4m plus 4, 4m plus 6, etc., 4m plus 12, which we must add to the existing sequences. Since each of these 5 new terms has even sequential number, we can write it as 2t. Then we can find the corresponding term in each existing sequence with sequential number t and increase the exponent of its denominator by 1 and add one new term with sequential number 2t and the exponent k plus 1. You can easily verify that the modified term in the existing sequence is replaced with 2 new terms whose sum is equal to the modified term. By the way, now we can explain why m cannot be less than 2. If m were equal to 1, then the smallest sequential number in this sequence of 5 numbers, 4m plus 4, would be equal to the half of its largest sequential number, 4m plus 12, and this would cause a problem for this algorithm. So we have proved that if m is not less than 2 and the proper sequences that satisfy the conditions of the problem exist for number 4m plus 1, then they also exist for number n equals 4m plus 13. So we need to show that these sequences really exist for numbers 9, 13, and 17. Then we can apply our method of mathematical induction, which will cover the entire set of integer numbers in the form 4m plus 1 and 4m plus 2. Since we have already shown these sequences for the first 2 numbers, n equals 1 and n equals 5. Here are the sequences for values 1, 5, and 9. And these are the sequences for numbers 13 and 17. This completes the solution of this interesting counting problem. Please feel free to write comments about the solution of this problem, especially if you have some ideas how to prove it more efficiently.